Welcome to the Deep Dive. Today we're venturing into an area where artificial intelligence is making some serious waves. Understanding and, generating the intricate world of molecules.
Right.
We're talking about potential breakthroughs in, everything from designing new drugs to crafting advanced materials. It's a really exciting frontier.
Absolutely. I mean, for a long time, a major hurdle in these fields has been just the immense computational power needed to accurately simulate how molecules behave. Especially when you're looking at the quantum level, it's incredibly demanding.
Right. So our goal today, our sort of mission, is to explore how leading AI researchers are tackling this challenge. We'll be digging into some fascinating new research papers and an announcement from Metafair.
Their fundamental AI research group, yeah.
Exactly. All introducing innovative AI techniques and, crucially, significant new data sets designed to make molecular modeling much more efficient and, more precise.
Kind of streamlining the whole process.
Yeah, think of this as your shortcut to grasping the cutting edge of AI in molecular science. We're aiming for those aha moments without getting too bogged down in overly technical details. Okay, let's unpack this.
Well, that's good. Our first stop is a paper titled Adjoint Sampling, Highly Scalable Diffusion Samplers via Adjoint Matching.
Okay.
What's particularly interesting here is the introduction of a new algorithm called, adjoint sampling.
Right.
This algorithm is designed to learn these things called diffusion processes. Think of diffusion processes as a way of gradually transforming one state into another.
Okay, like morphing something.
Exactly. In this case, it's about sampling from complex energy functions. These functions describe how molecules tend to exist based on their energy. It's related to the Boltzmann distribution.
Where molecules prefer lower energy states, right?
Precisely. They're more likely to be found in those lower energy configurations.
So instead of trying every single possibility, which is impossible, they're teaching AI to learn the most likely pathways or shapes for molecules to exist. That sounds much more, intelligent. What's the core innovation with adjoint sampling?
Well, the main advantage is its on-policy approach.
On policy?
Yeah. To draw a quick analogy, it's sort of like a student learning directly from the practice exams they take themselves, rather than just relying on theoretical lectures.
Ah, okay. Learning by doing.
Exactly. This allows the algorithm to learn and improve based on the samples it generates itself. And this leads to significantly more updates to the model, more learning for each actual energy calculation or molecular sample it needs to perform.
So more learning bang for your computational buck, essentially.
That's a good way to put it. It offers a major increase in scalability, allowing researchers to tackle much larger and more complex molecular problems than before.
And here's where it gets really interesting for me. They're not just relying on bigger computers. Right. They're fundamentally changing how the AI learns. The paper mentions a theoretical basis in stochastic optimal control. What does that mean in practical terms?
Well, that theoretical foundation provides a really robust mathematical framework for the algorithm.
Okay.
It basically ensures that the AI can learn effectively without needing extra tricks or, corrective measures to force its generated samples to accurately represent the real molecular distribution.
So it's more stable.
It's a more stable and maybe natural learning process. And what's more, they've cleverly incorporated the real-world physics of molecules by including symmetries and periodic boundary conditions. This is crucial whether you're describing a molecule's shape in standard 3D space, that's Cartesian coordinates, or by the rotations around its bonds, which are torsional coordinates.
Yeah.
You need to respect that underlying physics.
Got it. And it wasn't just theory, right? They actually tested this out.
Oh, absolutely. They demonstrated the algorithm's effectiveness on well-established sort of classical energy functions first. But what's compelling is how they then scaled it up to more complex scenarios using neural network-based energy models.
Right, using AI to model the energy itself.
Exactly. This allowed them to perform what they call amortized conformer generation across many different molecular systems.
Amortized meaning?
Essentially, they're training a single AI model to predict the likely 3D shapes, the conformers of a wide variety of molecules. So instead of painstakingly calculating the energy landscape for each new molecule from scratch.
Which takes ages.
Right. Researchers could leverage a pre-trained model to get a good starting point much, much faster.
That could really speed up things like the initial stages of drug screening, couldn't it? Sifting through possibilities.
Definitely. Train once, apply many times. That does sound like a significant efficiency boost. The paper also discusses something called reciprocal adjoint matching, or RAM. What's the big deal with RAM?
RAM.
Yeah, the reciprocal adjoint matching objective is basically a simplified version of their original approach. What's fascinating here is that they discovered a way to create a much simpler loss function for training the model.
Simpler how?
Instead of needing the entire detailed history of how a molecule changed over time in the diffusion process, RAM only requires snapshots of molecular states at two different time points, say the state now and the state one step later.
Okay, just pairs of states.
Just pairs, xt and x1, as they put it. This simplification dramatically reduces the computational cost of training.
Less data to crunch for each learning step. Makes sense. They also mentioned open sourcing a new benchmark. Why is that important for the wider scientific community?
Oh, that's huge, because sharing tools like this is absolutely crucial for progress.
Right.
A new benchmark provides a common standard, a common test track for researchers everywhere to test their methods and compare how well they're doing in this vital area of scalable sampling for computational chemistry. It helps the whole field advance more quickly together.
Yeah, everyone playing by the same rules, pushing the limits.
Exactly. And they provided detailed performance comparisons against existing, state-of-the-art methods, things like PIS, DDS, log variance, and IDEM.
On standard tests like DW4 and Leonard-Jones.
Precisely. On established benchmarks like DW4 and these Leonard-Jones potentials, LJ13, LJ55, what's really interesting is that adjoint sampling showed competitive and often superior performance.
In what way?
In terms of things like path ESS, that's basically a measure of how efficiently the algorithm explores the important molecular configurations, the important shapes.
Okay.
And also W2 distance, which is a way to quantify how different two sets of molecular structures are, how close are the generated shapes to the real ones.
Got it. And it did this better.
And it achieved this with significantly fewer energy evaluations. Remember, those energy calculations are the expensive part.
Right, the bottleneck we talked about. So better results with less computational costs, that's a clear win.
Definitely looks promising.
They also applied this to generating conformers using smile strings. Those are like the text codes chemists use for molecules, right? How did that work out?
Yeah, this is where the practical implications for fields like drug discovery become really apparent. They trained their adjoint sampling method to take a smile string, that text code as input, and then generate likely 3D conformations.
So text in, 3D shapes out.
Pretty much. They evaluated this on the SPICE and GM drugs datasets, comparing their two versions, Cartesian, using 3D coordinates, and torsional, based on bond rotations, with the well-established RDKit ETKDG method.
Okay, and they used recall and precision as their metrics.
Yeah.
Just remind everyone, recall here means how well the method finds the known correct conformers.
Capturing the true diversity.
And precision means how many of the shapes it generates are actually good, low-energy, plausible structures.
Exactly, and the results. They indicated that adjoint sampling, particularly the Cartesian version, after it was pre-trained and went through this post-generation optimization step called relaxation.
Relaxation, like letting the structure settle into a low-energy state.
Precisely. That version showed improved recall compared to RDKit.
So it found more of the right shapes.
It was better at finding a wider range of relevant conformers, which is crucial for exploring the vast possibilities in molecular design. They even introduced a new benchmark specifically for finding these stable, low-energy conformers from a given molecular energy model using a highly accurate pre-trained energy model called ESN.
It's interesting that they explored both Cartesian and torsional representations.
Yeah.
Were there significant differences in how they performed?
Well, initially, without pre-training, the torsional approach actually showed better precision and recall.
Oh, okay.
But after they pre-trained the Cartesian model and applied that relaxation step, it actually outperformed the torsional method.
Huh. Why might that be?
The researchers suggest this might be because the unconstrained nature of the Cartesian representation, just moving atoms in 3D space, allows for a more diverse exploration of the molecule shape, even if it starts from a more random initial state. Torsional is more constrained by bond angles.
Interesting trade-offs there. Okay, so adjoint sampling looks like a really promising and importantly efficient new way to explore the shapes molecules can take.
A powerful new tool in the toolbox.
Definitely. Now, let's switch our focus a bit to the data that these AI models learn from. Metafair recently announced a massive new data set, didn't they? This sounds like a pretty big deal.
Yes, this is a very significant development. Huge, actually. The blog posts and the accompanying paper, the openmolecules.pdf, they detail the Open Molecules 2025 dataset, or OMol25.
OMol25.
But what's truly remarkable is its sheer scale. We're talking over 100 million density functional theory calculations.
100 million.
Yeah. DFT, that's a powerful computational method scientists use to understand the electronic structure of molecules and predict their properties. And these calculations were done at a very high level of accuracy.
Wow.
This represents, they estimate, billions of CPU core hours of computation.
Billions. So with this level of detail and breadth, researchers hopefully won't have to spend nearly as much time generating their own high-quality training data that could free up a huge amount of resources, right? Accelerate progress.
That is exactly the idea. And it's not just the scale, it's diversity is key.
Diversity in what sense?
Well, OMol25 uniquely combines elemental diversity. It includes 83 different elements from across the periodic table.
83. Okay.
And chemical diversity. It covers a wide range of interactions within molecules, between molecules, the effects of solvents, different charges and spins.
So different chemical environments.
Exactly. And it also has significant structural diversity, so different conformations of the same molecule, and even structures involved in chemical reactions.
So it's not just a massive collection of similar molecules. It's designed to be broadly representative of the chemical world we actually encounter.
Precisely. It includes small molecules, crucial biomolecules like proteins and nucleic acids, complex compounds containing metals, think catalysts, and electrolytes, which are vital for research into things like batteries.
A really wide spectrum.
And these aren't just tiny systems either. Some contain up to 350 atoms, which is significantly larger than what's typically found in comparable data sets.
Okay, so what was the main motivation behind creating OMol25? What gap were they trying to fill?
Well, the primary motivation was the lack, really, of comprehensive, high-accuracy data needed to effectively train machine learning models.
Right.
Train them to act as reliable and fast substitute surrogates for those computationally expensive DFT calculations we talked about.
So the AI learns to approximate the expensive DFT results, but much faster.
That's the goal. The idea is that well-trained AI models can approximate DFT results much more quickly, enabling large-scale virtual screening and simulations that were previously just impractical.
So OMol25 is like a giant, meticulously curated training library for AI in molecular science.
That's a great way to put it. A foundational library. And they didn't just randomly generate molecules either. They used sophisticated sampling strategies.
Like what?
Things like molecular dynamics simulations to see how molecules move over time, various techniques for exploring different molecular shapes, and even a method called artificial force-induced reaction, or AFIR.
AFI.
Yeah, it's designed to specifically capture how molecules change during chemical reactions to map out those reaction pathways.
Ah, okay, not just static structures.
Right. And they also went back and reevaluated existing community data sets using the same high level of DFT theory, the same ruler, basically to ensure consistency across the entire OMol25 dataset.
That consistency is important for training reliable models. Now, rigorous calculations are obviously essential for a dataset this ambitious. What specific level of theory did they use? You mentioned it was high accuracy.
They employed the OB97MV functional paired with the def2tzvpd basis set.
Okay, that's quite a mouthful, but standard in the field.
Well, that specific combination, OB97MV with def2tzvpd, is widely recognized as one of the most accurate general-purpose DFT approaches currently available for a broad range of chemical problems.
So top-tier calculation.
Yes. They used the ORCA software package, employed advanced techniques to speed up the calculations where possible, and used very strict convergence settings to really ensure high-quality results. They even implemented rigorous quality control and error checks to filter out any problematic calculations. Quality was paramount.
Makes sense. If the data's noisy, the model learns noise. And to demonstrate the value and utility of this data set, they trained some baseline AI models on it, didn't they?
Yes, exactly. They evaluated several message-passing graph neural networks. These are common types of AI for molecules, including their own ESE model and another one called MCE.
Okay.
And importantly, they adapted these models to take into account the charge and spin of the molecules, which is crucial given the diversity within OMol25. Those properties really affect behavior.
Right. Can't ignore charge and spin. What kind of tasks did they use to evaluate these initial models? What could they predict based on the OMol25 data?
The evaluation tasks covered a really wide range of common objectives in computational chemistry. Things like predicting the strain energy within molecules.
How squished or stretched a molecule is.
Kind of, yeah. Also ranking different shapes of a molecule by their energy, calculating how easy it is to add or remove a proton, that's protonation energy, or remove an electron ionization energy.
Okay, fundamental chemical properties.
Right. Determining energy differences between different spin states of a molecule, and even assessing how well the models capture interactions at different distances, both close-up, short-range interactions, and interactions between atoms far apart, the long-range ones.
And what were some of the key findings from these initial evaluations? Where did the models do well, and where were the challenges?
Well, the model showed promising results on many of the tasks, definitely validating the dataset's utility. However, that distance scaling evaluation highlighted a significant challenge.
The long-range interactions.
Exactly, accurately capturing long-range, non-covalent interactions. Things like van der Waals forces acting over larger distances. Current baseline models, which often rely on a cutoff distance, they only look at atoms within a certain radius.
Right, to save computation.
They struggled when interacting parts of a molecule or molecular system were further apart than that cutoff.
So they're missing some of the physics further out.
It seems so. This points to an important area for future development in these types of AI models. How do we get them to see further, essentially?
Are the researchers suggesting any specific architectural changes to these models that might address this?
They don't go into deep specifics in this overview paper, but it clearly flags it as an area needing attention. It might require different types of message passing or attention mechanisms that can handle longer range dependencies more effectively.
Okay. But despite these challenges, the fact that this massive high-quality dataset, OMol25, is now publicly available, that's a huge step forward for the field, isn't it?
Absolutely. It's a game changer. OMol25 is released under a very permissive license, CC BY 4.0, meaning people can use and build upon it freely.
That's great.
And they're even making the weights of their baseline models available under a commercially permissive license.
Wow, even the models.
Yes. And they're also planning to launch a public leaderboard. This will undoubtedly spur further innovation by allowing researchers worldwide to compare their models directly on a standardized, high-quality benchmark.
That's fantastic. So now researchers around the world can easily compare their new methods, see what works, build on each other's successes, contribute to pushing the boundaries of the field together. That kind of open collaboration feels like a real engine for innovation here.
Couldn't agree more. It democratizes access to this level of data and evaluation.
Okay, so we've explored a powerful new sampling method in adjoint sampling and this incredible treasure trove of data in OMol25. Now, the third piece of our puzzle today is a family of models called UMA, or Universal Models for Atoms. What makes them stand out? What's the universal part?
All right, UMA. The UMA, a family of universal models for atom.pdf paper, introduces a novel approach to building these atomistic neural network models. The core idea behind UMA is to achieve high accuracy across a very wide range of chemical domains.
And it's universal.
Exactly. By using a clever architecture called MONE.
MOBE.
Stands for Mixture of Local Experts.
Ah, mixture of experts. We've seen that concept used quite effectively in large language models recently. How does that apply here to the world of modeling molecules?
It's a similar principle, actually. MONE combines the predictions from multiple specialized subnetworks, these experts.
Okay.
But the key is how it combines them. It does it based on certain high-level characteristics of the system being modeled.
Like what sort of characteristics?
In the case of UMA, these characteristics include things like the elemental makeup of the molecule, what atoms are in it, its overall charge and spin, and even information about the specific DFT task the training data comes from.
So it looks at the molecule and the task and says, okay, for this job, I need these experts.
You could think of it like having a team of specialists for different types of chemistry. Maybe one expert is good with organic molecules, another with metal complexes, another with reactions. And the model learns which expert or combination of experts to consult based on the molecule's overall features.
So the model can effectively route different types of molecular systems to the experts that are best suited to understand them. That sounds potentially very powerful.
Exactly. They also introduced a new way of representing the atoms in UMA, a new embedding that allows for the inclusion of charge, spin, and the specific DFT task directly into the model's understanding at the atom level.
Okay.
And this representation is used both for the atom-level predictions and for determining how to weigh the contributions of the different experts in that MOLI architecture. It informs both the local calculations and the global expert mixing.
Got it. What are the advantages of using this MOLI approach, especially when you're trying to train models on these huge, diverse data sets like OMol?
Well, the paper demonstrates that MOLI is particularly beneficial for multitask training.
Multitask means?
Training a single model on data from many different chemical domains or DFT tasks simultaneously, instead of training separate models for everything.
Right, a universal model goal.
Precisely. They found that UMA models with MOLI consistently outperformed models without MOLI that were trained on the same diverse data sets.
Okay, so the expert mixing really helps.
It seems so. Often, the MOLI models even achieved comparable results to models that were specifically trained on just a single, more focused data set or task. This suggests that MOLI helps the model learn more general and broadly applicable representations of chemical principles, rather than just overfitting to one specific area.
That makes sense. They also experimented with the number of experts in the MOLI architecture, didn't they? Did they find a sweet spot? Is more always better?
They did. Their experiments with varying the number of experts in their smaller UMA model showed significant improvements in performance as they increased the number of experts up to a certain point. They observed that the gains started to level off after around 32 experts in that specific setup. So it suggests a balance needs to be struck between the model's capacity to learn more experts, means more parameters, more capacity, and its efficiency. Adding experts adds computational costs too.
Right, always that trade-off. Efficiency is always a key consideration with large AI models, especially if you want to use them for actual simulations. How does UMA perform in terms of computational efficiency during use, during inference?
Yeah, this is another significant strength they highlight for UMA, even though these models can have a large number of parameters overall because of the MOLI architecture.
All those experts add up.
They do, but they've developed a technique to essentially pre-merge the weights of the relevant experts at the time you want to make predictions.
Pre-merge.
Yeah, so based on the input molecule's features, it figures out the right mix of experts, combines their parameters into a single effective network before doing the calculation.
So at runtime, it doesn't feel like you're running dozens of separate models.
Exactly. It means that during actual simulations or predictions, the model behaves much like a standard non-MOE network in terms of speed and memory usage.
That's clever.
It is. They show that UMA models can achieve state-of-the-art accuracy across many different areas while remaining highly competitive in simulation settings. They even mention being able to handle systems with tens of thousands of atoms on a single graphics card.
Wow, that's pretty impressive for a universal model.
Definitely opens up possibilities for larger scale simulations with high accuracy.
Okay, and finally, they briefly mentioned a heat of formation referencing scheme. What's the idea behind that? Seems like a detail, but maybe important.
It's about making the energy predictions comparable. Given that the OMol25 dataset and other training data inevitably come from various slightly different DFT settings or computational parameters.
Right, not perfectly identical calculations everywhere.
They implemented a referencing scheme based on the calculated heat of formation of individual atoms in their standard states. The goal is essentially to subtract out a consistent baseline energy for the constituent atoms.
Okay, why do that?
To make the relative energy predictions from their UMA models more broadly useful and potentially comparable to results obtained with slightly different DFT methods or settings that other researchers might be using, it tries to put everything on a more common energy scale.
Got it. Standardizing the energy 0 point, in a way.
Something like that, yeah?
Okay, so to summarize our deep dive today, because we've covered a lot of ground. First, adjoint sampling presents a really promising and crucially scalable method for learning how to sample molecular configurations, understanding the shapes molecules can take.
A new way to explore that energy landscape efficiently.
Right. Then, the Open Molecules 2025 dataset, OMol25, offers an absolutely massive and diverse resource, a real treasure trove for training the next generation of AI models in molecular science.
Yeah, unprecedented scale and diversity in public DFT data.
And finally, UMA introduces a clever architectural approach, using that mixture of local experts, MOLI, for building universal models that can achieve high accuracy across a really wide range of chemical tasks while still being efficient.
putting it all together, better methods, better data, better models.
Precisely. The potential impact of these advancements, on accelerating scientific discovery is truly immense, isn't it?
Oh, absolutely. Imagine the ability to rapidly screen billions of potential drug candidates computationally, or design entirely new materials with very specific desired properties, catalysts, battery components, you name it all, through efficient and accurate computational simulations powered by these AI breakthroughs.
It really does feel like we're on the verge of maybe not a revolution, but a significant acceleration in how molecular research is done.
A step change, potentially.
Yeah. On that note, here's a final thought for you, our listener. Considering these AI breakthroughs, the new ways of sampling molecular space like adjoint sampling, the sheer wealth of high-quality data like OMol25, and the development of more versatile AI architectures like UMA, how might these fundamentally reshape the entire landscape of molecular research? Think about how we design novel materials or search for new therapeutics in the coming years. How different might that process look?
It's definitely something to mull over. The tools are getting rapidly more powerful.
Indeed. Well, thanks for joining us for this deep dive. We really encourage you to explore the linked research papers and the blog post, and keep an eye on the progress being made with that open-sourced benchmark and the upcoming OMol25 leaderboard.
Yeah, exciting times ahead in this space.